Hello, my name is Arjun Rao and this is the project that I have created during the Institute's Technical Summer Projects. This is an attempt at creating a system capable of polyphonic sound generation, meaning that it should be able to play more than one notes or tunes at the same time. A normal keyboard that you find will probably be able to play 4 notes at least together, which is necessary for any musical instrument. So we decided to create a sound system that is capable of such features, and the design of our project is given over here. The main features of what we have done is that it has a circuitry capable of registering more than one key presses, meaning you press multiple keys, it will play multiple notes, hence satisfying the fact that it's a polyphonic synthesizer. We have achieved the interfacing of a memory card with the Atmega microcontroller, and this is also one of the features of the project, one of the things we learned during the project. And we tackled the problem of getting a good quality sound, which is translated as a high sample rate. So we developed a good coding algorithm that was capable of giving a good sound, and in order to create multi-instrument patches, in order to give the sounds of different instruments, we also studied the processing and replication of real-time sound waveforms. So like in any project, the project consists of 4 main stages, that is the input, processing, coding and output. The most challenging amongst this was the input stage, because we needed to design from scratch a system that would enable us to register multiple key presses. A simple way of doing this would be simply to connect all the keys to the existing microcontroller or the computer, so to speak, and take all their signals, decide which one is on, which one is off, and then play the notes accordingly. But this is not feasible because in an extended setup, considering 12 or 13 or 20 keys, we will not be able to connect 20 input pins to the controller because the controller has a limited number of input ports. So it is necessary to encode the input from the pins into binary format, as in supposing key number 17 is produced, the output should be the binary value of 17. This way we will be able to encode 20 inputs into 5 bits. 5 bits is easily put into the microcontroller. Now the problem with encoding is that we will not be able to represent combination of keys in 5 bits. For example, for 20 keys, the number of combinations of 2 keys is 20C2, which is well beyond the capacity of 5 bits to represent. So we have developed a system that, along with encoding, allows us to generate an input of multiple key presses. A key component of this design is this circuit over here. I have called the circuit a pulse generator, simply because when a switch is either pressed or released, as in the voltage goes from high to low or low to high, this circuit generates a single pulse. As you can see here, it goes up and comes down and stays down. This is important because this separates simultaneously pressed signals. As in, you press key 1, it generates a pulse. You press key 2 after key 1, key 2 generates a separate pulse, a pulse that is different from pulse 1 and is sent at a different time. This way the microcontroller can take in sequences of pulses and hence judge which key is open and which key is closed. For instance, if you press key 1, it will send a pulse and the microcontroller will know that key 1 is open. Then you press key 2, it will send a pulse and the microcontroller will know that key 2 is open. When you release key 1, it will send another pulse, thus telling the microcontroller that key 1 is closed. Hence the microcontroller can register multiple key presses and play multiple frequencies at the same time. The next stage we have is the processing stage. This is the stage by which we develop the sound waveform and process the input data to give the output. The problem which we faced, as earlier I had mentioned, is that we needed a high sample rate, which requires the fact that our entire waveform be stored on the RAM of the microcontroller. So what we have here is our algorithm for developing the sound. I have expressed interest in playing instrument patches, as in the sounds of various instruments. So the algorithm which I have used for that is this. The waveform for any particular instrument, that is waveform as a single wave starting from 0 to 2 pi of that instrument, is broken down into 1024 samples in time. Each sample is of 1 byte each, as in it can go from 0 to 256. 1024 such samples which are stored in a memory card, an SD memory card, which is interfaced with the Arduino microcontroller. The waveform here is scaled in time to achieve different frequencies. So what we mean by scaled in time is simple. If 1024 samples are played at a sample rate of 1024 samples per second, then we will get a waveform of 1 hertz. Supposing you skip samples, play alternate samples one after the other, that means you will play the entire waveform in half the time it took to play earlier. This means that you have doubled the frequency. Hence, using this sort of algorithm, we have generated frequencies by scaling the waveform. The scaling involves rounding off because the samples are discrete, they are not continuous. However, the inaccuracy is negligible because 1024 samples for one waveform is an extremely high wave density. The next part that we have here is coding structure. In the coding structure, a very important concept which we have used, a concept which is integrated within the microcontroller, is called interrupts. An easy way to understand this is, when you press a key, a note plays. But when the note is playing, you touch another key, we expect that both of them play simultaneously now. However, we know that when we press the key, a pulse is created, and when the pulse is created, it must be registered by the microcontroller. So the microcontroller is already processing the sampling of the sound, and also it has to take the input. So how do you make the microcontroller perform two simultaneous tasks? The question is, this is not possible. However, we can make the key press interrupt the existing processing, that is the sampling. We can make it interrupt that and register the input. After registering the input, it can start the playback again. Hence, the inputs are taken in the form of interrupts. This allows interrupts to be registered within the framework of a music being played already. So the next thing is, how have we sampled the sound? What steps have we taken to ensure that the sampling of the sound is done at a very accurate rate? The sampling rate has to be very accurate, otherwise the frequencies will be distorted. So that we have done using another concept known as a timed interrupt. A timed interrupt in the Arduino microcontroller is something that is set off at a very periodic interval which can be set. This directly decides the sampling frequency, and this gives the sampling rate. Inverse of the sampling frequency gives us the sampling rate. The sampling rate which is used in this is of 20,000 hertz, around 20,000 hertz, which is a substantially good sampling rate considering the fact that the Arduino microcontroller is not a very powerful microcontroller. Also, the waveform discussed above, the waveform mentioned over here, 1000 samples in 1 byte, is read into the RAM during setup time, as in before we play anything, the 1024 samples are read in about 1 or 2 milliseconds into the RAM, and from there on the processing takes place. The final part of our project is the output stage. The output stage is relatively simple. It is simply a digital to analog converter, as in the 8 bits that you see over here are the digital output from the Arduino. The Arduino gives the 8-bit samples taken from here continuously at a given sample rate, and that is converted by this into its corresponding voltage level over here. So this voltage level is fed into an audio jack, into this audio jack, which will play the sound which is given by the given waveform. In the making of this project, we faced many challenges. Some of the major ones are listed here. The Arduino is a relatively weak microcontroller, and in order to achieve a high sampling rate, we had to substantially improve the algorithms, the methods that we use to process the sound, and I believe we have done a good job on that, in considering the fact that the sample rate is more than 20,000 hertz. And the second one is designing the input system capable of registering multiple keys that we have mentioned here, which involves the pulse generator. And the last one is erratic input pulse due to bouncing of keys. This implies that when you press a key, the contact is not very clear. The key will bounce off its contact many times, leading to tremendous amount of noise. This noise can severely affect the performance of the instrument, and in order to reduce those noise, we have introduced something known as debouncing circuitry. Debouncing circuitry has been introduced for each of the keys in the synthesizer in order to reduce this noise. However, we have not been completely successful in eradicating this. So what are the advances can be made to this project? What are the improvements possible on this? Extending the system to incorporate more keys. The input here, like our current project over here, has only 4 keys. We have made a prototype of 4 keys. However, our input system here is capable of easily generalizing itself to holding many more keys, much more keys, up to 20 keys, 20 or 30 keys. So if anyone is interested enough, he can easily incorporate more keys by replicating the circuitry. And as I said, this was not completely eradicated, and so effective debouncing of the keys is one aspect which can be looked into. And the last piece is including circuitry to enable choosing of the instrumental patch. As I mentioned here, I wish to play a particular instrument. However, we can see that the waveform is read only during setup, so only a particular instrument is being played by this synthesizer. So an expansion to this would be including circuitry to enable the choosing of an instrumental patch from a list of patches. This exercise has taught us a lot regarding regarding the functions and the capabilities of the Arduino microcontroller, and the Fourier analysis, the Fourier analysis and the sound analysis that we did prior to the project has taught us a lot about the nature of sound and the nature of instrumental patches. The design of the algorithm has tested the algorithmic skills, the patience in coding. We have learnt a new language, the language programming of the Arduino microcontroller. And so all in all, I would say that this project has been an extremely satisfying learning experience, and I definitely know a lot more than I would have if I hadn't done this. That's all I have to say. I'm sorry, the demonstration is not really possible because it's on an earphone, and I really can't show earphone on the camera. So that's it for now, and thank you for listening.
So this is 2RE05 drum beats replicator. Our main aim was to prepare an electronic drum kit, wherein when you hit a particular part of a drum with a drumstick, it produces that respective sound with an intensity that is proportional to how hard you hit that drum part. So our main objective was divided into 2 parts. First was to play a sound file and detect which part of the drum kit is actually hit in the sound file, and then we glow that part of the drum by LEDs. The second part was that the person sitting on the drums will hit that drum, and then that sound will be replicated again. So the first step wherein we play the sound, we have used piezo sensors on each and every drum part. There is an Arduino code that reads the value of the piezo sensor, and then that value is given as an input to the processing code. Processing code and Arduino code, both of them have been used simultaneously, and the 2 of them have been connected by serial processing. Next, the step 2, basically it's for sound filtering and LED glowing. Whenever a sound file is played, the processing code detects which part of the drum kit has been played in the sound file, and then that particular part of the drum glows by a series of LEDs which have been placed in parallel. And for each and every different drum kit, there's a color coding of the LED. Each and every drum part has a different LED. Just a signal for me. Now the designing of the drum kit. The materials used. In the first place, we used a piezo sensor. A piezo sensor basically detects the pressure. On the basis of how hard you press that sensor, it gives an analog value. Okay, so next up was the plastic plates. For making any part of the drum, we used a plastic plate. On the top of it, we had an aluminium plate on which we had a piezo sensor. Above it, we had a layer of foam and cotton, and to cover it all up, we had canvas cloth. Okay, the main use of aluminium sheets was that if we hit the drum part on any other place other than the place where the sensor was placed, this aluminium plate transfers those vibrations to that sensor so that it is able to detect that pressure. Also, to create a proper mount so that it looks like a proper drum kit, we had acrylic plumbing rods. We cut them into pieces and then we developed the entire drum kit. The steps involved again were, there was a sound file. After that, we applied the code of sound filtering, which is where we could detect which part of the drum kit was being played. Up next, via the Arduino, we glow up those respective LEDs. Next, the person who's the drummer hits the drum part and then sound is produced via that processing code. And that sound produced has a controlled volume on the basis of how hard the drummer hits the drum. Once again, we are Drumbeats Replicator. The team members are me, Kriti, Ridhima, Milan and Sagar, and our mentor was Asha Tejwani.
Hi everyone, I am Deepak and I am a BTech second year mechanical engineering student, and this is my project ENO that I have named it as ENO 2.0. So this is my project ITS for ITSP 2012, and this is a quadruped dog. So it has 4 thigh joints and 4 legs. I have been using 9 servo motors for this project, and 8 are for the movement of the joints and 1 for the neck joint. This is using a infrared sharp sensor. This can measure distance from 20 to 150 centimeters, and I have been using Atmega 328 as my microcontroller, and I'll just give a small demonstration of so what actually this is doing is, it is right now searching for objects, and when it gets any object in the range of less than 60 centimeters, it follows the object. Like right now it is following my leg, and if I move away from it, it again tries to follow me. And this even this can even perform autonomous tasks like walking in different styles, taking a 0-point turn, and like moving sidewards. It can even perform vector motion so that it can move in a 45-degree line. So it can perform jumps of 3 types, and it can even sit in many possible positions, and it is a So actually the so actually the searching algorithm is like it searches in an angle of 0 to 180 degree angle span, and it starts searching from 0 degrees it's like it searches in an angle of steps of 3 degrees and 3 degrees. So actually it searches in the first 3 degree, searches for the object, and it doesn't get any object, it searches for another 3 degrees, and any point if it searches for an object less than 60 centimeter in its range, then it sends an angle theta to the microcontroller. So actually the voltage, the output coming from the sharp sensor is in the form of a voltage in between 0 to 5 volt, and what I do is I use a calibration formula to calibrate it in the form of centimeters. So I get the values from the sharp sensor in the range 0 to 150 centimeter with an error of 2 to 3 centimeter. So in this case, when it searches for an object, the loop changes to a follow loop. So in this case, the R and the theta value that it generates are used for generating parameters for it to follow the object. Generally the parameters are like the left thighs are controlled with a parameter called U, and the right thighs are controlled by a parameter called V. So R and theta are manipulated in such a way that we get proper values of U and V so that the bot itself decides what radius of turn, how many steps and what turns it has to take in order to reach the object. So that is the searching algorithm and all. And for moving sidewards in a vector motion, what I've did is just a parameter kind of a motion. So if I put the parameter 30, 30, it moves front with a medium speed, and if a parameter changes to be 20, 30, then it takes a differential turn with a specific radius. So this is how the turning process and all takes place.